Okay, we're going to be looking at section 9.3 today, and we're going to get a new notation where we're going to be looking at using the symbol y dot, which you guys may see in engineering or physics. This equals a function that depends on y and t. And in this notation, we can write y dot instead of dy dt. So basically, y dot is a stand-in for dy dt. So our first example is going to kind of use this notation. They're going to give us a function or a differential equation that says y dot equals y minus t, and they want us to draw the slope field. And we can interpret this as dy dt equals y minus t. This should mean the same thing as y dot equals y minus t. So how we draw a slope field is we basically look at a bunch of different points. I'm going to just kind of look at, we'll only do this for like going out to 1 and 2 instead of going out to like 5 or something. So basically what a slope field is for each intersections, we're going to use this expression here, and this is going to tell us what the slope of the line is at the point, or the slope of the equation is at the point, and then we'll try to draw that a little line segment with that slope at the point. So basically, at all these individual points here, we're going to try to draw little line segments that have the slope of our line there. To speed this up, we can do something which is called find isoclines. So basically, for an isocline, we set what we want the slope to be. So for example, if we set the slope equal to 0, that would mean dy dt is 0. So we get 0 equals y minus t. And this is our t-axis, this is our y-axis. So if we solve this by adding the t across, we would get t equals y. So every point where the t value and the y value are the same, those all have slope 0. So like 1, 1, the t and the y are the same, we'll draw a little line segment with slope 0. 2, 2 gets slope 0. 0, 0 gets slope 0. Negative 1 gets slope 0. And negative 2 gets slope 0. So this is sort of the isocline for c equals 0. If we looked and said, well, what about c equals 1? So we would say, all right, the slope is going to be 1. That'll equal y minus t. So we can add the t across and say 1 plus t is y. So anytime your y value is 1 bigger than your t value, that will have slope 1. So here my t value is 0. So when my y value is 1 bigger than 0, which would be here, 0, 1, my slope is 1. So if my t value is 1, 1 plus 1 is 2. That gets slope 1. If my t value is negative 1, then 0 gets slope 1. And if my t value here is negative 2 plus 1 is negative 1. Those all have slope 1. So basically, the diagonal row of points right above the ones that was all zeros, those all have slope 1s. And we can kind of see, well, if we had c equals 2, that would say 2 equals y minus t, which would say if your y value is 2 above your t value, those have slope 2. So I draw slope 2. It's going to turn out this whole diagonal row will have slope 2. And you guys probably can guess that this one up here is going to have slope 3. And this one here will have slope 4. And if we do the same thing down here, these will all have slope negative 1 if you're down below this. Again, we could say, all right, let's let c equal negative 1. That would be negative 1, the slope equals y minus t. Add the t across. So whenever your y value is 1 less than your t value, so if my t value is 0, my y value is -1, I have slope -1. If my t value is 1, my y value would be 0. My t value is 2, my y value is 1. My t value is 1, my y value is -2. Those all have slope -1. And it's going to turn out the next one down has slope -2. The ones after that have slope -3. And the final one would have slope -4. So this right here is basically our, this is our slope field. So we defined this, we kind of said, let's figure out where everyone's 0, let's figure out where everyone's 1. If we weren't sure about that, alternately, we could say, like, we could have gone through and point by point, like, let's say we use the point 1, 1. I could have plugged the 1 from the t value in, the 1 from the y value in. So 1 minus 1 is 0, and I could have generated it that way. And I could have gone through point by point and plugged in for t and y here and see what the slope was. But when you do that, you have to go through and do like 1, 2, 3, 4, 5 by 5. So you'd have to plug in 25 different points. When you do it this way, like when c was 0, we kind of got 5 points all at once instead of just 1 point. And then we got like 4 points here and 4 points there, and then that was enough to kind of see the pattern. So doing it the isocline method can speed things up a little bit, but if you're just like, I don't know what the slope should be, you could take you could take your points and you just plug in the t and the y value into there and see what it gives you back, and that would be the slope that you draw. They want us to do one other thing with this slope field. So we say, okay, here is our slope field that we generated. They want us to sketch the integral curves. So for this example here, we have the slope field that we just generated. They want us to sketch integral curves through, or I guess we say not through, but we would say with initial conditions. Part A, we get y of 0 equals 1, and part B, we get y of 1 equals -2. So for this first one, we'll put the point when t is 0, y is 1. So that has our point B right here. And we use the slope field to kind of draw out, and it'll tell us how our point basically draws. So if we start drawing, we head off in the direction with slope 1, and we bump into the next part here, which also has slope 1. If we go in this direction, we have slope 1. We bump into the next one that also has slope 1. So if we have the initial condition of y of 0 is 1, we basically all just hang out on this line here of every point we bump into as slope 1. So it just makes this straight line, and that would be our answer for the part A. For part B, they say, what about if y of 1 is -2? So y of 1 is -2. That would be down here on this point. Well, here we start out with slope -3. We're going to lessen through stuff that's -2. Then it goes kind of to 0. And then it's going to approach like that. So we kind of use the slopes around it to approximate what our line does. So the slopes are getting shallower, so my line gets shallower. Here the slopes become 0, so my line needs to kind of become 0 when it's along this diagonal line. Then the slopes will start getting more negative and will approach like that. So this would be our answer to part B. You kind of use the direction that the slope curves go to kind of, you place your point, you use the slope field around it to kind of approximate where your line is drawn. Let me pull up real quick one of these from the AP test, and then we'll look at a couple more of these. So this is from the released stuff on the AP test. That's I put that at the top of the modules, so you all can go there. So here's like an example of kind of a free response, one of these on the AP test. They give us dy dx, so they're using dy dx is y squared over x minus 1, and they want us to draw the slope field for these 6 points. So since there's only 6 points and there's not 25, I'm just going to use, instead of trying to find isoclines, I'm just going to use the points themselves and plug them into the equation. So let's start with 0, 0. If I put 0 in for y, I get 0 squared over 0 minus 1, which is 0. So we would have our first point there is 0. Then I would have 0, 1, and 0, 2. So if I have 0, 1, I get 1 squared over 0 minus 1, which is 1 over negative 1, which is negative 1. So when I'm at the point 0, 1, if I plug that into this equation here, I get dy dx is negative 1. So this one here, I draw a little line segment with slope negative 1. For 0, 2, I get 2 squared over 0 minus 1, which is 4 over negative 1, which is negative 4. So at 0, 2, I need to try to draw a line with slope negative 4. Okay, so halfway done. Now I have 2, 0, 2, 1, and 2, 2. So for 2, 0, I plug 2 in for x and 0 in for y. So I get 0 squared over 2 minus 1, which is 0 over 1, which is 0. So down here I have slope 0. 2, 1, y is 1, so I get 1 squared over 2 minus 1. That's 1 squared over 1, which is just 1. So at this point here I have slope 1. And then when I get down here to 2, 2 squared over 2 minus 1 is 4 over 1 is 4. So this point here will have slope positive 4. And so on the AP test, for some of the slope field stuff, this is an example of that you might find. And again, in our classroom, to show you all where I put released AP stuff up here. Here's stuff about the test format and date. Here's stuff about the some of these older AP tests that they released. Let me try to find one other real quick here from this that involves the slope field where you draw an integral curve. So here's the one that we want to look at next. So they give us a bunch of extra stuff that we're not going to use at the moment. And this is going to be kind of the process where I drew these lines in. This is what our problem here is going to have us do. So here's our equation. They want us to draw the integral, okay, so portion of the slope field, the differential equation is given below. Sketch the solution curve through the point 0, 1. So solution curve and integral curve are kind of the same thing. So solution curve through the point 0, 1, that's x value 0, y value 1. Here's the point. So our slope field, we have kind of steep slopes that shallow out. So we would start drawing. It's going to be kind of hard for me to draw this, but we'll say draw steep slopes that kind of shallow out. Then they get steeper again and more steep. So our first part's kind of doing something like that. Then we have steeper slopes that get really steep, and then they kind of start to calm down, and then they kind of go off like that. So some sort of shape like this, you try to use the slope field to predict the direction. So we placed our point, then we used the slope field lines to kind of approximate our curve that way, and use our slope field lines to approximate the curve down there. And something like that would be another thing that you see maybe on the AP test that involves involves a slope field, in this case solution curves or integral curves. So we're going to do another example with this from our textbook. So they say the temperature y of t, which is in degrees Celsius, of an object placed in a refrigerator satisfies the equation y dot equals negative 0.5 times y minus 4. And in this equation, t is in minutes. We want to draw the slope field and describe the behavior of the solutions. So draw a slope field and describe behavior of solutions. Okay, so to draw the slope field, let's put we're going to try to do this by isoclines again. So kind of looking at this, if we look for c equals 0, and we look at our equation right here, to make this y dot 0, I would have to put 4 in for t. So every point that has a y value of 4, those all have slope 0. So we have 0, slope 0 here, slope 0 here, slope 0 there, slope 0 there. So let's look and see if your y value was 5. So every point that has a y value 5, 5 minus 4 is 1. 1 times negative a half. Let's say it this way. All points with y equals 4, y equals 4, those all correspond to c's equaling 0. All points with y equals 5, those give us back, we put 5 in here, 5 minus 4 is 1, 1 times negative 0.5. All those points have negative 0.5 for their slope. So those are all shallow slopes of negative a half. So everybody that has a y of 5, you have negative a half for the slope. If your y value is 3, 3 minus 4 is negative 1. Negative 1 times negative 0.5 is positive 0.5. Your slope is positive 0.5. So everybody with a y value of 3 has positive 0.5 for a slope. Everybody with a y value 2, 2 minus 4 is negative 2. Negative a half times negative 2 is positive 1. So that'll give us at 2. All of our points have y value 1. And then we probably can guess at y equals 1. We put in here 1 minus 4 is negative 3. Negative 3 times negative 0.5 is positive 3 halves, which is 1.5. So that would be a little bit steeper yet. And so this is kind of what our slope field is going to look like. We could do more if we wanted to, but we kind of can see this is what the slope field looks like. So what happens is if you place an object at a given time, so time is along the x-axis, this is the y-axis. If I put an object in here that's above 4 degrees Celsius, this will cool it down till it approaches 4 degrees Celsius. If I put an object in here that's under 4 degrees Celsius, this will raise its temperature until it reaches 4 degrees Celsius. So describe the behavior of the solutions. We'll say y values above 4 will approach 4 as time increases. And we'll say this represents a warm object being cooled. to, I guess we'll say 4 degrees Celsius. And if we have y values below 4, these will approach 4 as time increases. And this represents a object below 4 degrees Celsius being warmed to 4 degrees Celsius. And so from this we can conclude the refrigerator is set to 4 degrees Celsius. So regardless of what you put in there, the fridge will either, as time increases, the fridge will either drop the temperature down to 4 or it'll raise the temperature up to 4. And basically, since the fridge is set to 4 degrees Celsius, anything you put in there, if you let time go on long enough, it will eventually approach 4 degrees Celsius. Okay, the last thing that we need to talk about is this idea called Euler's method. And what this basically says is we're going to use this formula, y of k equals y of k minus 1 plus h times f of t of k minus 1 up to y of k minus 1. So basically what we're going to do here is we're going to define something h called a time step. And what we're going to do is we're going to have a starting point, and we're going to use this formula to take, say when time increases this much, we're going to extend out a certain direction given by this formula. And then the next time step, we'll look at the formula that'll have us extend another bit for the next time step, and the next time step will extend again further. What it would kind of look like is if you had a curve like this, you would be approximating the curve by taking little steps, and each time you get done with your step, you reevaluate what direction you want to go. And so you're kind of trying to approximate the curve by a whole bunch of small line segments. This one's easier to see with an example how it works. So we're going to do the Euler's method example here. And see, it's not too bad. It's just kind of taking these incremental steps. So for example 3, we want to use Euler's method with time step. And that'll be h equals, so time step is h equals 0.2. And we want to take 4 steps to approximate. They're going to give us a function, approximate a solution, or the solution, I guess we should say, through or of y dot equals y minus t squared. And they have the initial condition y of 0 equals 3. So what we're going to do is we're going to say, okay, our initial point, t of 0, is going to equal the initial time, which is 0. And y of 0 will be the y value at 0, which is 3. So this is kind of our starting information. Since h is 0.2, we're going to be using a time step of 0.2. So we want to figure out what is y1, which is going to be the y value after our first step. So we're starting here at kind of 0, x value 0, y value 3. And we're going to take a step that's, say 1 is out here. And we have 1, 2, 3, I guess I need an extra tick mark, 4, 5. I guess actually it was okay if I had it earlier. So like here's 0.2, here's 0.4, here's 0.6, and here's 0.8. So if we have that, we're going to say we start here at this 0.03. We're going to figure out where 0.2 is, and that'll tell us where the first step is, and then we'll use that to determine the next step, and we'll use that to determine the next step. And that's kind of the process we're going to use to get through this, is we're going to be finding the y value at each time step. So y1 is going to equal, from our formula, it'll be y of 1 minus 1, so that's y0, plus our time step. And then it's the function at 1 less than the current number you're on. So our function is y minus t squared. So this will be y0 minus t0 squared. So we use our equation here. And we use for the subscripts, we use 1 less than the number that we're on. So plugging stuff in, y0 is 3. The time step is 0.2. y0 is 3. And t0 squared, t0 is 0. So we'll put that all into a calculator. And that's going to give us back 3.6. We get back 3.6. So then we say, all right, y2. We're going to go all the way up to y4 because we're doing 4 steps. So y2 will be the y1 value plus the time step of the y1 value minus the t1 value squared. So y1 is 3.6. Our time step in this case is still 0.2. Our y1 value we just found was 3.6. Probably box that in because that's our first value they asked us to find. And the t1 value, well, when you were here at the initial t, you were 0. At the one point, you had taken 1 time step. So this will be a 0.2. And if we type this into our calculator, that'll be about equal to 4.3. So we'll say it's about that. It's not actually that, so we can put a little squiggle equals. Say that's about 4.3. So y3 would be the y2 value, which is 4.3, plus the time step, which is still 0.2, times our y2 value, which is still 4.3, minus the previous time squared. So when we were looking at y2, the previous time was 0.2 because we had only taken 1 step. Here we've taken 2 steps, so t2 would be 0.4. It's 2 time steps down. So if we type that into our calculator, that'll be about equal to 5.14. And the final one will be y4, which is going to be based off of y3, which we just said y3 was 5.14. Plus our time step, which is still 0.2, times our function evaluated at the previous step. y3, we just figured out y3 was equal to 5.14. And at t3, we've taken three time steps. Each time step is 0.2, so 3 time steps would be a 0.6. And if we plug that into our calculator, we'll get a 6.1. And then that's basically how we could use Euler's method to calculate and approximate our function. What it would kind of look like is we would start here at 3. Let's say here's 0, here's 0.2, here's 0.4, here's 0.6, here's 0.8, and here's 1. So we started at 0, 3. That was the t equals 0 value. Then one time step down, we were at 3.6. So one time step down, we were about here. Then when we went another time step, we were at about 4.3. Should be like there. Then at 0.6, we were at 5.14. It's a little bit beyond there. Draw a straight line between them. And then at 0.8, we were at 6.1. So 6.1 at 0.8. And so if we just kind of connected stuff, this would be our Euler method approximation to whatever the curve actually looks like. So it's built up of these 4 line segments. And you probably could see from this, if you wanted to be closer to what the actual curve is, instead of using 0.2 for a time step, you might use 0.02. And instead of only taking 4 steps, maybe use a computer and take like 1,000 steps or 2,000 steps. And then that would be a much more accurate graph. So this is a method of using Euler's method to kind of approximate a solution to that function through there. And what we would actually be building if we had the slope field, we would actually be constructing one of these lines through the slope field for that function using Newton's approximation is what, or sorry, not Newton's approximation, using Euler's method. So we'll stop there, and that's it for 9:30.